All right, everybody. So this is a test for goodness of fit test. So this is a type of hypothesis test that we're going to do for a frequency distribution. Okay, so it's unlike the other ones we've done so far. So what it means by testing for a frequency distribution is, we're going to see does the given frequency follow what we expect to actually happen. That's essentially what a goodness of fit test is all about. Okay, this is very popular when it comes to businesses and finances because as you go along in the future, you want to see is this trend going to happen as to what you expect to happen at this point in time or in the future when it comes to it. So it's pretty big as we get closer and closer to the end of the semester, where this is more happening into life scenarios itself. Okay, so unlike the other ones, which is a good thing, is we actually have a template for this type of test. Okay? And what I mean by a template is they're all going to be the exact same process. Okay, so for our null hypothesis, it's going to be a sentence, not an actual notation mark. It's an actual sentence. Okay, and that sentence is going to be always be the proportions of the claim are all the same. So we're assuming all the proportions will be the same. Okay, but again, we have to say this in words, not in actual notation purposes system. And again, you'll see an example why that's true. Okay. And for alternative hypothesis, is always going to say at least one proportion will not be the same. Okay, we don't know which one, but one of them is not the same. Okay, that's what I mean by one is not expected than the other itself. Okay, again, this is an intro class, so we'll just do at least one. You get far more in detail once you get to higher stats when it comes to it. But for now, we're just briefly introducing the topics themselves. Okay, so that's always going to be our null alternative hypothesis. It's going to be the same. At least one is not the same. Okay? And again, we're always going to relate it back to the question itself. Okay? Now, when it comes to our test set, again, it's going to be a chi-squared value, so nothing really brand new. We know what a chi-squared value is. And even better, it's always a right-tailed test, which is a great thing. So it's never a two-tailed, left-tailed. It's always a right-tailed test for a goodness of fit test. Okay. Now, just like the other hypothesis testings, pretty much the only difference between one and the other is basically how to find your test stat, right? So even though it is a chi-squared value, how to calculate it is going to be very different. Okay. So this is going to be our test statistic right here. It's O minus E squared divided by E. And remember, this is a sum. And I'll just break this down so you can see what's going on. So O means the observed value. So what we found up in our frequency distributions. E is going to be what we expected to happen for each individual frequency. Now to find E is very simple. It's always N times P, where N is the total number of frequencies, and P is the probability of each frequency class. And again, that's also pretty easy to deal with as well. In most cases, the P value is going to be 1 divided by how many categories we actually have, unless otherwise told to us. And you'll see that in a little bit as well. Okay. And the last thing is going to be K, which means the number of classes/categories in our frequency distribution. Okay. So in other words, you can kind of pretty much P is 1 over K, because that's how many classes we actually have itself. So this can really break down to E is equal to N times 1 over K when it comes to it. Okay. Now we also have K minus 1 degrees of freedom. So this is the only one that's going to be a little tricky. When we calculate our critical value, it's always K minus 1, so the number of categories minus 1. Okay. So which comes to our critical value, we use the same thing as the chi-square distribution. We use an alpha and degrees of freedom, which is going to be right here. Okay. And then finally, we just state a conclusion based on itself. Now, in this one, we don't have to do the chart. All you're going to do is literally state which one is true. So if we fail to reject, you're going to copy exactly our null hypothesis. If we reject, you're going to copy exactly our alternative hypothesis. So it can be one or the other when it comes to our conclusion. Okay. So let's try an example so you guys can see what's happening here. Okay. So it says a wedding caterer randomly selected clients from the past few years and recorded them. Assuming you want to test the claim that weddings occur in different months with the same frequency, use a 0.05 significance level. Okay. So here's our frequency distribution: January, February, March, April, May. And here is the numbers we found for this caterer found for the months, the wedding portions. Okay, so for our null hypothesis, we go back. It says we're always assuming the proportions are the same. So we're going to be assuming the proportions of weddings that occur in different months is the same, meaning it's the same, 50-50, 20-20, so forth down the line. And in this case, since we have 1, 2, 3, 4, 5 categories, it's going to be 1 over 5. So we're assuming they're all the same proportion. It happens 25% of the time, or 20% of the time, no matter what fund we're actually in. Okay, so that's what I mean by P is just 1 over the K, number of values, proportions we have, 1, 2, 3, 4, 5. Okay? And then our null alternative hypothesis as at least one, so notice I'm just copying it down, so at least one proportion of the claim is not the same. So at least one proportion of weddings that occur in different months is different. So notice it's very similar, right? Just a little couple of words difference when it comes to it, and that's always going to be the case when it comes to a goodness of fit test. Okay. Next, we're going to find our test stat. So to find our expected values for each individual case, it's going to be 1 over 5 times the sum of our frequencies. So if we just add all these up, that should give us 42, and we just multiply, that gives us an expected value of 8.04. Okay. Now, if you see, all I did is just break it down. So I put the months down here, the numbers here, that's going to be observed, and the expected values is E is going to be down here. Okay. Now, since we're online, I'm going to give you guys a little help, right? We don't have to do this all because, you guys are online when it comes to it. Usually, if you're in a class, you would have to do this work when it comes to it. In other words, break down the actual equation itself. But since we're doing online, I'll give you guys a break. We're going to use a website to help ourselves out here. And here's the website. We're going to, once you click on the link, you're going to go down here and just going to put it in. So notice we only have 2, and it's just insert row. So we need a total of 5 of them because we have 5 classes, right? 1, 2, 3, 4, 5. And we're going to input our observed and the expected values themselves. So we have 5, 8, 7, 9, and 13. And you can customize this. You can say this is, January, but it's not required if you don't want to. And then the expected value, they're all the same going down the line. And now you're just going to calculate, and your chi-squared value is right here, 4.19. And notice that's what you get if you just do it manually. And there we go. Right. So that's how we're going to find our test stat, and you can do this for the homework as well. Okay. So that gives you that, and then now we're going to find our critical value. So degrees of freedom is 1, 2, 3, 4, 5 minus 1, which is 4. Our alpha was in this question 0.05. So if we just go to our table, 0.05 with 4 degrees of freedom gives you 9.488 is our critical value. That's what we get there. And therefore, since it's not in there, we do not reject. Okay? So if we do not reject, therefore, our alternative is correct. So you literally just copy that down. Notice I said the proportions of weddings that occur in different months is not the same. Oh, it is the same. Sorry, that's right. What am I talking about? We do not reject, so the null hypothesis is correct. Oh, I don't know what I was talking about there. So it's the same. There you go. So literally just copied my null hypothesis, and that's your conclusion there. Okay. Pretty straightforward when it comes to it, just like the other ones. As long as you're able to do this, you just smooth sailing when it comes to it, figuring out your critical values as well. Okay. So let's try one very similar to this one is here. So same situation. The only difference is I just gave you guys an extra values to see when it comes to it. So let's try this out. So null hypothesis is the proportion. Yeah. Is exactly that. The proportion of weddings occur in different months is the same. So it's going to be the same as above since it's the exact same question. All I did was just add a tune to it so you guys can practice with it. So this one is the same thing. Okay. This one, however, you got to be careful of because our P is going to be a little different. So our P in this case is 1 divided by 1, 2, 3, 4, 5, 6 this time. And our N, again, is just going to add up all the numbers together. So get our calculator out and just add them all up. So 5 plus 8 plus 7 plus 9 plus 13 plus 20 gives us a grand total of 62. So therefore, our expected value in this case is going to be 62 times 1 over 6, which gives us, just plug in the calculator, 62 times 1 over 6, 10.33. Okay, and then at this point, right, we're just going to plug it into our website. So we're just going to add a category in this case, make this 20, and we got to change all these to 10.33 instead. Calculate, and there we go. So our chi-squared value is 14.263. So if we go back over here, step 2, right, because that's going to sort of test that. Is our chi-squared. What was it? 263. Okay. Next up, we want to find our critical value, see if we reject or do not reject. So to find our critical value, our degrees of freedom in this case is going to be 1, 2, 3, 4, 5, 6 minus 1, so that's 5. And alpha was given to be 0.05. So again, right, we just go to our chi-squared distribution and see what our critical value is going to be, with 5 degrees of freedom and 0.05 as our alpha. So that is 11.070. So again, it's a right tilt test, so we want everything greater than this one, but unfortunately, that's a no, right? So we, again, do not reject. H naught. Okay, so therefore, when it comes to our conclusion, so if you guys want, right, this is step 1, this is step 2, and then finally step 3, when it comes to our conclusion. So we're just going to copy exactly which one's correct. So if we do not reject, so therefore our null hypothesis was actually correct to begin with. That the proportion of weddings occur in different months with the same frequency is correct. It is the same. Okay, and there we go. That's how we're going to do a goodness of fit test. So let's try the next one. So question 2 says, when considering effects from eliminating the penny as a unit of currency in the U.S., they randomly selected 100 checks and recorded the cents portions of these checks. Use a 0.05 significance level to test the claim that the 4 categories are equally likely. Okay. So let's write a null alternative hypothesis. Okay. So null hypothesis is the proportion of, and what we're talking about, pennies, right? So the recorded proportion of recorded pennies of these checks is the same, right? Is the same for all categories. Right, since we're on categories, yeah. Alternative hypothesis is at least 1. Is different. Right, so very similar, right? But once we have one, you automatically have the other one itself, okay? All right, that's step 1. So now we go on to step 2 to find our test stat. So in this case, first we're going to do is find P. So to find P is, well, how many categories? 1, 2, 3, 4. So this is just 1 over 4. And we want n, so n is just the sum of everything, but they give us that, which is nice, which is just 100. So our expected value is 100 times 1/4, 100 times 1 over 4, 25. Okay. Well, next up, now we're just going to go to our table to find our chi-squared value, right? So now we go back over here. Since we have 4 categories, just delete one. So we have 61, 17, 10. And then finally 12. And these are all 25. And there we go, 70, it's a whopping 70.16, right, when it comes to it. Okay, next up, we want to find our critical value. So same process, we got to find degrees of freedom, which is 1, 2, 3, 4 minus 1 is 3. And same alpha, I believe, right, 0.05, yeah. So we just copy this alpha here. So our critical value is going to be, going back over here, 0.05, going down to 3, 7.815. And this time we definitely reject, right? Because this is way past, because it's a right tail test. So we definitely reject the null hypothesis. So our conclusion is definitely at least one is different than the other one. And there we go. Okay. Right, so let's do one more. And I want to show you guys when, what if you're given a little bit something tweaked up when it comes to it. So this one says, if you're a baseball fan, it's an interesting question for you guys. This one says, the table lists the number of games played in the World Series. The table includes the expected proportions for the number of games in a World Series. Use a 0.05 significance level to test the claim that the actual number of games fit the expected probabilities. Now, here are the number of games. So if you're in the World Series, right, it's best out of 7. So this is when you swept somebody, you won the first 4 games, you won 5 out of the, 4 out of the 5 games, you won 4 out of the 6 games, and you guys went, tied at 3-3. You won the last game, right, when it comes to it. So these are the actual observed values. Now these are the expected values. So these for each individual portion, these are P's individually. So what that means is we're going to have 4 different E's depending on which proportion we're actually given. So remember, our expected value is equal to n times P. Or this time, this P is different for each individual case. Okay, so we just got to keep that in mind when we talk about that. All right, so let's try it. So first thing, find our null hypothesis. So the proportion of the number of games in the World Series is the same for each game. Alternative, at least one is different. Okay. Right, so next up, we're going to find our test stats. So again, like I said earlier, P is going to be different for each one. So P is exactly these ones themselves. So all we have to do is find N. So N again is the sum of all of them together. So just add them all up. So 19, let's start a calculator. So 19 plus 21 plus 22 plus 37 equals 99. Okay. So to find our test stat, so a chi-squared value, we have to do a little bit of calculation ourselves to begin with, right? So let's just write, so we have 4 data values here. So this first one's going to be, you can just clear everything if you like. So 19, 21, 22, 37. And now to find this expected value, for instance, it's going to be 99 times 2 over 16. So that one's 12.375. And that's how you do the rest of them. So the next one's going to be 99 times 4 over 16. So 24.75. And we can do the rest, right? So next one's 5. Okay, press calculate. And there we go. There is our chi-squared value. Okay, so 7.885. Right, so now we got to find our critical value. So degrees of freedom in this case, again, is going to be 3. 1, 2, 3, 4 minus 1 is 3. Alpha is, again, 0.05. So it's going to be the same one we've done a while, 7.815. And we barely reject, right? But it's enough to reject. Because again, it's a right tail test, so it's higher. So we definitely reject, even though it's barely rejecting, but still enough, right? So therefore, we know at least one of the proportion of the games is different. And there we go. We finished our hypothesis test for goodness of fits.